Audio. Christy's with us. Yay, Christy. And there we go. Tuesday, September 15th. That looks pretty good. There we go. That's today. Okay. And we have, I think I pushed chat by mistake. Let me push this participants. We have Nicholas and Christy so far. That's good. Did you guys have any questions or comments for me that you can think of?
Not offhand.
That's fine. Now tonight, the topic is capacitors. We're going to study capacitors. It's chapter, I don't know, we've been studying chapter, yeah, it's chapter 8. We're going to study chapter 8. And we're picking up some more wonderful students. There's Phoebe, Christian.
Hi.
Hey, hello. And I guess just the three of you guys so far. So we're just waiting for some more of our students. I got all of your tests graded, and I'll let you look at them Thursday night. And I put the lab on Blackboard. You could study that lab and get some of it done. Let me see. I'll show you what it looks like. It's called. Hey, we got some more. We got Daniel. Daniel, he's with us. Good deal. This is what this lab looks like, and it's on Blackboard, and it's called Experiment 11. It's actually going to be our 5th lab, I think. Is that right? No, it's our 4th lab. This will be our 4th lab, but this says Experiment 11. It's capacitor discharge. And we'll do that. There we go. That's what it looks like. You have that on Blackboard. You could pull it up. It's on, I've got 2 sides. There's another side on the back. You could do a few things to get started. There's only one equation. And you could do the dimensional analysis on that. And what do they call it? The definitions, yeah. Variable definitions. You know, when you do your lab, let me find this lab report form thing here. Lab report form, where are you? Here we go. Yeah. Here's a lab report form. There's a thing called equations. Well, there's only one. You could write, you could have some of your work done when you walk in. There's equations. And then there's variable definitions. You could write down get this copy of this lab, write down the different variables there. there's only four or five different variables. And when you do that, you're supposed to write the symbol of the variable and then the name of the variable and then the units for the variable. And then you could do the dimensional analysis for the equation. You could have that all done before you ever come in. Let me just go over that. See, there's a name, and there's a symbol, and there is the unit. Like, for instance, there's electric field. And the symbol is E, and the unit is newtons per coulomb. And there is, what else have we studied? I don't know. There's something called electric flux, yeah. Electric flux. Symbol is this Greek capital letter phi, and the units are Newton meters squared per coulomb. And we could keep on going. There's 1,000 of these things. Maybe not in this one course you're taking, but there's names, there's symbols, and there's units. I want you to know them for everything that we study. Well, I've got 5:30, and I think we should get started. The topic is capacitors. So while we're at it, why don't we write that down? There's something called capacitance. And you could look that word up in the dictionary. I think it just means how much, like a bucket. What is the capacity of your bucket? How many gallons will it hold? Only for this class here, capacitance is how much charge something will hold. We're not filling a bucket with water. We're filling a capacitor with charge. And the symbol for capacitance is C, and the unit is a farad. And you could write that with a little F-A-R-A-D if you wanted to, or if you write it like that, you have to use a capital F. And what the definition is for capacitance is it's the amount of charge that you have divided by the amount of volts that you have. So what that is coulombs per volt. That's what a farad is. A farad is a coulomb per volt. This is the defining equation of a capacitor. And of course, you can take that equation and play with it. You can write the voltage as Q over C. And what's the other way of doing it? You could write the charge as C times V. It's just algebra, right? You can do that. And we'll do that. But I thought I'd show you how you could make a capacitor. There'll be some, you'll be using some actual physical capacitors Thursday night in the lab. But I thought it'd be fun to make one. And what you need is you need two pieces of metal. A capacitor has two pieces of metal. And I'll just use this, I've got some tin foil here, well, it's really aluminum foil, isn't it? It's not tin. It's aluminum foil. It's all wrinkled, but that's okay. And so let me, I didn't bring my scissors, but I've got a knife here, and I'll cut out a couple of pieces. I don't want one this big. Okay, I'm going to cut out a couple of pieces now. Cutting out a couple of pieces of tinfoil. There, I cut out one piece. It sort of looks like Oklahoma, only the panhandle is a little bit too long. But I need two pieces. You have to have two pieces. So here, let me cut out another piece now. There, I cut out another piece shaped like Oklahoma.
What does Q stand for?
Oh, thanks for asking. Q stands for charge. You've seen it before in Coulomb's law. But thank you for asking. It's the charge, and see, it's in coulombs. See what's confusing? Here's why I like to put, and who was that, by the way, that just asked me that?
Zach.
Zach, thank you so much. Here's why I like to put units in brackets, because look, there's a C right there. See it, Zach? And there's a C right there. Those are different. That C right there stands for coulombs. It's a unit of charge. That C right there stands for capacitance. It's not a unit. It's a quantity, kind of like a distance or time or temperature or a whole thousand other things, but it's not a unit. See, these are units. Volts are units, coulombs are units, farads are units, and if you put them in brackets, you won't get mixed up, hopefully. Another one that you can get mixed up with is M and M with brackets. See, that M stands for mass, but that M stands for meters. Well, now back to my capacitor. I was going to make one. I made another Oklahoma-shaped. See, I got two of them. Look, ta-da! I got two Oklahoma-shaped things here. Now we're going to make a capacitor. And here's the secret. You don't want them to touch. If those pieces of metal touch, you don't have a capacitor anymore.
You have a short.
You have a short. Exactly right. So here's the dirty little secret. I'm going to insulate it with a piece of paper. Now let me do a little thinking first. I need to know how thick this paper is. So just one tiny minute while I think this over. I need to know how many sheets I have here. Just a second here. I'm going to count these sheets. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 10 sheets. 10 sheets of paper. And the thickness, I have a pad of paper here. It's almost all used up. But believe it or not, there are 10 sheets here. I counted them. There's 10 sheets. And the thickness of those 10 sheets, gosh, you got to have good eyes to see this, is about 1 millimeter. 1 millimeter. I've got a little ruler here. and you got 1 millimeter. So now if you have 10, if you have 10 sheets, and the thickness is 1 millimeter, then this is going to tell us how far between the plates they're going to be. See, if you have 1 millimeter and you have 10 sheets, I think the distance, if you just have one sheet, is 1/10 of a millimeter. That makes sense to me. It probably doesn't to you yet, but it will in a minute. Here's what we're going to do. We're going to take 3 of these sheets, and see if this makes any sense. I'm going to put this piece of Oklahoma here on this sheet. All right. And then I'm going to put this sheet on top of that. And then I'm going to put this piece of Oklahoma on top of that. And then the last sheet, let me find what happened to I had 3 sheets here. Yeah, okay, here we go. Now, the reason I made these panhandle on my Oklahoma strips is I need to have a connection. Capacitors have 2 wires coming out of them. And so these aren't wires, they're just aluminum strips, but I can connect those. I've got myself a capacitor. Now, let me pull back this one sheet so you can see. See, there's that piece of Oklahoma in that sheet. Now I'm going to pull back both sheets. There's that other one, see? But they're not touching. They cannot touch. They touch, you have a short, like one of my students said. Okay. Now we're going to figure what the capacitance is of my capacitor. Let me put it down for a minute. I just made a capacitor.
Hi, Papa.
Hey, bud.
I just wanted to say hi.
Yeah, good to see you. I haven't seen you for a while.
Yeah.
Give me a hug. My buddy. Yeah.
Where's your students?
Hey, just a minute. Where are my students? Hey, everybody say hi to my grandson, Gabriel. Gabriel, get over here so they can see you. Everybody say hi to Gabriel. Go for it. Say hi.
Gabriel.
Hi, Gabriel.
Okay, buddy. See you later.
Have a nice time, Papa.
Oh, we'll have a fun time. Now I want to show you this equation. I need a little room here. But we figured out those sheets are 1/10 of a millimeter. There's an equation I want to show you for capacitors, and it goes like this. That's how it goes. Where this D is the distance between your plates. You know this little epsilon 0 thing. You know that thing by heart. And the area. Oh, wait a minute, Auga. We didn't get the area of our plates. So let's do that. Got to have the area. What I'm talking about is this rectangular area. See, this here is just the connection. We have to have a connection. But I've got a ruler here, and it says it's 13 centimeters long and 10 centimeters wide. You can't see that, but I can. So I can get the area. Now let me put my capacitor back together there. Had to take it apart. See, the area we're talking about the area of the plates, the metal plates. All the paper does is insulate to keep them from touching. And I think I said it was 13 centimeters by 10 centimeters. I could almost do that in my head. Is it 0.0130 square meters? Did I do that right? Double check me. Double check me. Point 0.0130. No. 0.13 times 0.1. Yeah, of course it is. It's 0.0130. We could have done that in our head. So looky here. If you know this, and see, those plates are separated by one piece of paper. And that piece of paper is 1/10 of a millimeter, which is 0.0001 meters. That's 1/10 of a millimeter. Okay, now look, we know this, we know this, we know that, and I'm gonna derive that formula for you in just a minute. But get your calculators and find the value of that capacitance for me. Go ahead. I'm gonna do it, and then I'm gonna call on one of you. Find the value of that capacitor. Go ahead. Well, I got an answer. Let me pick on one of you guys. Let's see, I'll pick on one of my wonderful students. How about Stephen? Unmute and say hi.
Hello.
Yeah, hello. Stephen,
I had
have you done those yet?
to find that E sub 0.
Oh, that's okay.
I've got it. So
That's okay. It's 8.854 times 10 to the minus 12. Go ahead and put that in and tell me what you get.
I got a 1.505 times 10 to the negative 10.
How come I got 1.11 times 10 to the negative 10? Do yours again. This is 8.854.
Okay, I just did 8.85.
Oh, okay. Yours is okay. You just round it off. You're fine. But I bet that's right. Now you could write that. Well, of course, the units are farads. But see, you could write that as, well, if you made that a -9, that's a nano.
I'm getting 10 to the negative 9th.
Yeah, me too.
Okay, let me do it again. Just a minute.
And I got 1.15 times 10 to the negative 9.
Yeah, I got
that's
the same
what I
thing.
thought. Yeah.
I could be wrong, guys. It's possible. No, I didn't get that answer this time. Let me start all over again, just a minute. Now the area is 0.013 and the distance is 0.0001. Hey, I'm getting 1.15. Is that better? And that 10 to the -9?
Yeah, that's what I got.
How about other people? You feel better
Yeah,
now?
Yeah, that's better.
Good. I don't know what I did. So that's why I need you guys. Between you and me, we can do this stuff. Okay, now what I was going to say is that is a nano. And so you could say 1.15 nanofarads if you wanted to. That'd be fine. It's just fancier, that's all. But well, when we get our when we get our capacitors, they'll either be in nano or in pico. See, I tell you what that is. That's 1,150 picofarads. Because see, a pico is 10 to the minus 12. See, if you make that smaller, you got to make that bigger. And what we're going to be working with Thursday night, trying to think. No, I think they're microfarad. Never mind. But the farads, they come in micros, nanos, picos. That doesn't scare us at all. Okay, good. Now let me show you where this equation came from. And I need a little room here to work. Now be careful, that equation really only works for what they call parallel plate capacitors. You see, the symbol for a capacitor is a thing like this. Ta-da, you're looking at it. There you go. And this formula works great for parallel plate capacitors, which is basically what we had. Now let me show you where it comes from. It comes from this. We know the definition of capacitance goes like that. And we know that voltage is equal to ED if the electric field is constant, and it is. The electric field is constant inside a capacitor. In fact, the electric field is equal to sigma over epsilon zero. I think you've seen that formula before. I know, you've seen both of those formulas before. And now we're going to do a little algebra. Here we go. We are going to put Q over ED. All I did was just substitute for the V. You can handle that. And now that E, I'm going to substitute this here for that E. So you have Q over sigma over epsilon zero D. Okay, we're coming right along now. And so you got Q epsilon zero over sigma D. We're getting closer. We're getting closer, aren't we? Now, try to remember what this sigma is. What that is Q over area. It's the charge per area. So let's put that in there. We have the charge per area, epsilon zero. No, I'll get this right in a minute. We have Q epsilon zero, and then see this here is charge per area. There we go. Hey, look, the Q's cancel, and you're left with epsilon zero A over D. So this is a definition of what capacitance is. And here's two of your old equations that you know and love. And all I did was just put the three together and do a little algebra, and we came up with this beautiful equation for parallel plate capacitors. And we even solved it, and we got some nanofarads. Is there any question on that so far?
Nope.
No questions, okay. Well, here, I'll show you this. This is kind of big and cumbersome here. Remember, I made myself a capacitor. Now you understand. But see, what I'm going to do is I'm going to roll this thing up. Let me start from the other end. Here we go. You can't see what I'm doing very good, but I'm rolling it up. You could have made one a lot smaller. Ta-da! Now all I need there. All I did was I rolled it up. All I need is a rubber band to keep it from unrolling, or I could glue it, I suppose. And I've made a capacitor. Now the geometry is a little different. This is not exactly a parallel plate capacitor. It's more of a cylindrical shape, isn't it? It's not two flat plates. It's two curled up plates. But it would be interesting to measure this. We have capacitor checkers in the lab, but I can tell you it's going to be in this ballpark. It's going to be in the 1 nanofarad capacitance ballpark. So if you're marooned on a desert island and you want to make a radio, see, they have capacitors in radios, and you want to make a 1 nanofarad capacitor, all you got to do on your desert island is scrounge around for some aluminum foil and some paper, and you can make one. Trouble is, there might not be any aluminum foil. There's just probably a coconut tree and some coconuts, but it's worth a try. So we've tried to explain about capacitors. We don't want the metals to touch, but they don't. See, remember, there's a layer in between those two metals. They don't touch. If they do, you don't have a capacitor anymore. Any questions so far? Okay, let's see what's next. In your chapter, let's see where we are in our chapter. There's that equation right there. That you want to memorize that. That's the definition of what capacitors is. Hey, they made one on page 350, just like the one I made. If you look at it, they rolled it up, didn't they? And then, oh look, on page 353, they came up with this same equation that we have. And I showed you how to get it. There it is. And you even put it in your calculators. And I got it wrong, but you guys got it right. Now they have different shapes. They have cylindrical and spherical capacitors. And of course, you get a different formula when you have those. But our next topic is when you put capacitors in series and in parallel. So let me do that now, unless you have a comment or question. Okay, we're going to put them in series and parallel now. I just need some room here. We're studying capacitors. If you ever look inside a radio or a TV or a cell phone, they have capacitors in there. And you might ask yourself, well, what good are they? What do they do? And the answer is they store energy. Capacitors store energy. Remember that water bucket? It has capacitance and so many gallons of water. Well, capacitors have a capacity to store charges, and they store energy because there's energy associated with charges. That's what they're for. They're storing up energy. Now let's put some in series and parallel. Here we go. Now in series, here's a couple of capacitors in series. There we are. You could have more. You could have C1, C2, C3. Hope you can read my writing. That's supposed to be C1 there. Now there's something you need to know about. This is called series. Here, let's put some in parallel for you. This is called parallel. I think you've seen that before. I know you have with resistors. The thing about capacitors is the formulas are just opposite. See, if you had resistors, you just add them up. But if you have capacitors, the equation goes like this. Doesn't that look like the equation for resistors in parallel? See, if you have resistors in parallel, then you have an equation like that. I probably should draw that, but we've studied it before. But see, when you have capacitors in parallel, you just add them up. It's just the opposite. The equations, the form of the equations is just the opposite of the form of the equations for resistors. I don't know what to call this. The best name that I can think of is the equivalent capacitance. It's the equivalent capacitance. Let's put some numbers in there and we'll show you. Usually these things come in pretty small numbers, like maybe 6 microfarad and 3 microfarad. But you don't add them and get 9 microfarads. You have to do this. You have to go 1 over 6 plus 1 over 3, and you'll get 1 over, we'll put a question mark. I'm going to shut up and let you get that. Go ahead. Find what this equivalent capacitance is, and I'll be quiet for a tiny minute. Let me go to one of my wonderful students here. Find out if you guys are with me on this. How about Daniel? Daniel, unmute and say hi.
Hello.
Daniel, have you figured out what goes right here?
Yeah, it'd be 1/2, wouldn't it?
Yeah, good going. Good going. See, this thing here acts like a 2 microfarad capacitor. Do I have enough room to write down here? Not much. I think there's enough room. If you replaced these two with a 2 microfarad capacitor like that, you would never know the difference. They call this A and B. And this is A and B. You could take those out and replace it with a 2 microfarad capacitor, and you wouldn't be able to tell any difference. They'll store the same energy. The same charge will run in to the plates. It just behaves the same. But now, like if this is a 6 microfarad, and this is the 3 microfarad, these just add up. If you got 6 and 3, I get 9. You could replace those two in parallel with a single 9 microfarad capacitor, and you wouldn't be able to tell the difference. This will have the same charge that goes in and out of it. It'll have the same energy, the same voltage. You can't tell the difference because it's an equivalent capacitance. All right, let's show you where these equations come from. Now they show you in the book. You could read the book. It's all right there, but here, I'll go through it with you. Let's look at this series one first. Let me erase these now. Hopefully you understood that. What you need to know about series is whatever the charge is that goes into this. Here's some charge. It goes into this, and the charge goes on that plate, and it makes this plate minus because it repels positive charges, and they go to this plate, and that repels positive charges and makes that minus. What I'm trying to tell you is they have the same charge. Whatever the charge is on this capacitor is the same charge on that capacitor. If two of these pluses come in here, it repels two pluses and makes this two minuses. And those two pluses come to this plate, and that repels two pluses, and those two pluses go that way, probably to a battery, to a negative terminal on a battery. So the charges are the same, but see, these have different charges. When you're in parallel, you could call this Q1, you could call this Q2. They can be different. I tell you what's the same here is the volts. Whatever the volts is on this capacitor, you have to have the same volts on that. But these have different voltages. Whatever the volts is on this can be different than the volts on that. So what's the bottom line? Same charge, different volts. In parallel, same volts, different charges. It's important for you to know that. Now let's see if we can derive this. If that series capacitors are going to have an equivalent circuit, then whatever the voltage is on the equivalent circuit will have to add up like that, because you know, you have a voltage here, voltage there. We need to put some numbers in. But here's the way it works. C equals Q over V. So V is equal to Q over C. So this equivalent voltage will equal Q1 over C1. And this equivalent voltage will be Q2 over C2. Ah, but the Q's are the same, aren't they? There, you don't need a Q1 and Q2 when you're in series. They have the same charge. And you could write this voltage here as that same charge over what they call the equivalent capacitor. We're going to replace it with a single capacitor. Now we can do a little math here. You can just get rid of all those Q's, and here's what you'll have. Do a little math there. Now, if you had more than two in series, you could add some more. Hey, we just derived this equation. It's a nice little equation, but when is it good? It's good when you're in series. Did that show up? Yeah, that shows up. That's not too bad. Now in parallel, let's see if we can figure this out. The total charge coming into a parallel capacitors like that would be the sum of the charges. See, some of the charges come in here and go on this plate. But some of the charges come in here and they'll go on this plate. Okay, well that makes sense. Since this has got a bigger capacitance, you probably have more charges on that plate than on that plate. Okay, and you can see from this equation that Q is equal to CV. So we're just going to go C for the equivalent capacitance times the voltage equals C1 times the voltage plus C2 times the voltage. But remember, the voltage is the same when you're in parallel. You can do a little algebra now and just get rid of those voltages there. And you have your equation now for the equivalent capacitance. If you have more than two in parallel, then you can just add them like that. And if you didn't like the way I did that, read the book. We need to put some actual numbers on here, and then maybe we could work some problems in the book. Yeah, let's put some numbers on there. But first, do we have any comments or questions on what we've done?
Nope.
I'm sorry, say again.
No.
Okay, good. We must understand it, I hope. Well, let's go on then. Let me give you some examples with some numbers, okay? Well, there's one right there. It's got 3 microfarads and 3 microfarads and 6 microfarads, okay? Let me do that. Let's connect that to a battery. Let's connect it to a 6-volt battery. Now, what we want to know is what's the volts on that capacitor, what's the volts on that capacitor, and what are the charges? Of course, they're both the same in series. What are the charges on each capacitor, and what are the voltages? Okay. Well, the way you do these problems is you make your equivalent capacitor. And now we already did that, and we came out with a 2 microfarad. So see, this whole circuit can be replaced by this circuit here, where this is a 2 microfarad capacitor. Do you understand? That's the equivalent capacitance. If you forgot how we did it, we went 1 over C equals 1 over C1 plus 1 over C2. And we plugged in our numbers, and we got 2 microfarads. Okay. Now this is a lot simpler than that. Here, you can get the charge by just going CV. Memorize this. C is equal to Q over V. And from there, you can get Q is equal to CV. Well, we have the C and we have the V. It's 6 times C, that's 12. You know what? You've got 12 microcoulombs on this capacitor, don't you? And you have 6 volts. Well, that means you've got 12 microcoulombs on each of these. Let me write that. You have 12 microcoulombs on this one and 12 microcoulombs on that one. Now you can get the volts. See, here's the way the volts work. The volts equal the Q over C. What's 12 microcoulombs divided by 6 microfarads? Well, I get 2 volts. So this is 2 volts. What's 12 microcoulombs divided by 3 microfarads? See, to get the volts, you take your microcoulombs and you divide by your microfarads. 12 divided by 3, I get 4. We got 4 volts on here. Now do 2 volts and 4 volts add up to 6 volts? Well, yeah, that's what you got. And here's an interesting thing. 3 is smaller than 6, but the 3 is the little guy, and the little guy gets most of the voltage. It gets a 4 volts, whereas the big one only gets 2 volts.
Where did the 12 come from again?
Say that again, please.
Where did the 12 come from?
The 12. The 12
Yeah.
came from Q equals CV. Thanks for asking. The C is 2, and the V is 6. 6 times 2 is 12. See, the secret. Now, was that Zach? Is that who that was just now?
Yeah.
Zach, that was you, right, Zach?
Yeah.
Yeah. Zach, the secret to doing these problems is to draw an equivalent circuit, to simplify and find an equivalent capacitance. You have to use those equations. We found that this here acts the same as a 2 microfarads. And you understood that, didn't you, Zach?
Yeah.
Well, once you got this equivalent circuit, then you can just go to town. Q equals CV. 2 microfarads, some 6 volts is 12 microcoulombs. That's where the 12 microfoulombs, that's not right, microcoulombs. And of course, this has 12 microcoulombs because in series you have the same charge. Okay, well, let's do this one. Now, if you connected this, let me make a little room here. If you connected this to a 6-volt battery, the dirty little secret to doing these problems is to make a simplified equivalent circuit. See, if you add these together, you get 9. So you could make here a simplified circuit that looks like this, with just one capacitor, and it would be 9 microfarads. Because see, they just add up. They just add up. When you're in parallel, the way it works is they just add up. Okay, and this is 6 volts. So here we can get the charge. The charge is going to be CV. 6 times 9 is 54. 50, you're going to get 54 microcoulombs. The problem is that's the total. And it's going to be split up between the two. Now let's find out exactly how it's split up. Well, you know how it works. Q equals CV. If you got 6 volts and 3 microfarads, what's 6 times 3? It's 18. I like my, I was going to put it in a different color, but that's all right. I got 18 microcoulombs on this one. And I got 6 and 6. 6 times 6 is 36. I got 36 microcoulombs on this one. Now, does 36 and 18 add up to 54? By Jove, it does. 36 and 18 add up to 54. So we have the charge. We know the volts. It's 6. They both have 6 volts on them. The volts are the same in parallel. We have the charge. 36 microcoulombs, 18 microcoulombs. We have the volts, we have the charge, and we have the capacitances. Well, we need to do some more and practice that so you'll feel good about it. Let's go on. Any other comments or questions before we go on and tackle something else? Now we need to do a problem or two here. Let's stop and do a problem or two out of the book. Let me make some room here. We're going to do a couple of problems out of the book. Let me see. Let me see which ones I want to do. How about okay, I picked out some problems here. Totally organized. Yeah, here's one. This is 823. It's in your book. And we're going to do it. Here goes. You got to find it first. 823. All right, it says here, what capacitance is needed to store 3 microcoulombs of charge at a voltage of 120 volts? Let me write this down. We know we have 3 microcoulombs. See, that's the charge. We're doing problem 823. And the voltage is 120 volts. Well, we got the relationship. It goes like this. Look, they give you the charge and they give you the volts. And what do they want? They want to know the capacitance. Well, we can do that. You would take the 3 microcoulombs, you divide by 120. I can do that. 3 microcoulombs divided by 120 volts. You do it. You do it. I'm going to do it. We're going to find our capacitance. Go for it.
I have a question.
Yeah, go ahead.
When you work this one and you have the 3 over 120, do you still do the 3 times 10 to the negative 6th?
Yes, absolutely.
Okay.
I got my answer. What did you get? Now who was that I just talked to?
Christy?
Christy, right?
Yes.
Christy, did you get the answer yet?
Yeah, I got 2.5 times 10 to the negative 8.
That's what I got. Now what would be the units, Christy? Do you know what the units are for capacitance?
Yeah, it's farad.
Yeah, there you go. Now they pronounce it farads, but if you want to call it farads, you go right ahead. But it's everybody else out there says farads. Now you could, to make this more elegant, you make that 10 to the minus 9. Now that makes that smaller. And so what you get is 25 nanofarads. Because see, nano is 10 to the minus 9. Now I bet that's the answer. Let's look up the answer to see how we did. I'm going to go to the back now. And I'm going to shop around and I'm going to look up the answer for 823. 823. They said 25 nanofarads. That's what the answer book says. Yay, we did great. Any comments or questions so far? Okay, well, let's do some more. Let's do this one. We're going to do 825. Well, let me find it here. 825. Okay, just a minute. I lost my page here. 825. Here it is. The plates of an empty parallel plate capacitor of capacitance 5 picofarads are 2 millimeters apart. What's the area of each place? Each plate. Okay. Well, remember that lovely equation that I derived for you for parallel plate capacitors? It goes like that. In this problem here, this problem 825, they give you the capacitance. They say that it's 5 picofarads. Now, a pico is a 10 to the minus 12. That doesn't scare us. And we know what this is, or we should have it written down someplace. And the distance apart is 2 millimeters. So that would be in meters, 0.002 meters. So look at here, we know everything but the area. Now they're asking for the area, and I'm going to shut up for 1 minute, and I want you to solve this. We know everything except the area, and I want you to find the area. Go for it. Well, I wonder, let me pick on somebody here. Phoebe, my friend Phoebe.
Yes,
Uh, Phoebe, did you figure out the area yet?
no, I'm still putting it in because I figured out I didn't realize what pico was at first.
It's 10 to the minus 12.
Yes, I
Take your
have
time.
that now.
Take your time. We'll wait for Phoebe. You can do this. Go for it.
Is it 1.13 times 10 to the negative third?
That's what I got. The
That
area
would
is,
be a meter squared.
yes, it would be 1.13. That sounds good to me. Times 10 to the minus third meters squared. Good going, Phoebe. Now let's see if we got that answer right. I'm going to go to the back and check their answer book. We just did problem 825, and it says, 825. It says 1.1 times 10 to the minus third meter squared. They're just so lazy, you know that? They got 1.1 times 10 to the minus third. They did okay. They just, shame on them for rounding off. Our answer is better than their answer. Okay, that wasn't so hard. Well, let's see, maybe we'll do another one. These are nice. Pretty easy, I guess. Let's do this one. This is, no, let's hold off on that one. I'll do that in a minute. Let me tell you about energy. Now, I told you the purpose of capacitors is to store energy. What's amazing about them is they can store energy and give that energy back 1,000,000 times a second, more than that. Like on my radio, what's KCFO? Does anybody know? Is that 1300? Is KCFO 1300 kilohertz? Don't quote me on that. I'm a little bit rusty. But there's capacitors in my radio. If KCFO is 1300 kilohertz, there's capacitors that can store energy and give it back 1,300 kilohertz. You know what that is? That's 1.3 million times a second. They can store energy and give it back. Store energy and give it back 1.3 million times a second. That's what capacitors can do for you. But let's come up with the equation now for energy storage. Now, there's actually 3 equations. Now, this book likes to use this U symbol here for energy for some reason. It's really electric potential energy. And what you're doing is you're storing energy in an electric field. And one of the equations goes like this. There's actually 3 of them. And I'd like to show you where they come from in a minute. And then there's this 3rd one that goes like this. Now, I did all these from memory, which is kind of dangerous. Let's make sure I haven't goofed up, okay? And this would all be in your book here someplace. It's on page 366. Did I get these equations right? Boy, Jove, I did. Those equations are all correct. Let me show you where they came from. Then we can figure the energy stored in a capacitor. If you plot voltage versus charge in a capacitor. Here's your capacitor. And let's say it's empty right now, kind of like an empty bucket, and you start pouring water in it. Well, it starts to fill up. Only we're not pouring water in a bucket, we're putting charge into the capacitor. And here's the equation. The equation goes like this. Of course, this is what you're going to memorize. The definition of capacitance is Q over V. But if you want to solve for V, it's Q over C. Well, C is just a constant. C is a constant. Once you make your capacitor, remember I made one earlier. It's starting to unravel, unfortunately. There it is. Remember my wonderful capacitor with my Oklahoma Panhandle connections? Once I made that capacitance is a constant. Whatever that is, it's in the neighborhood of I think a nanofarad, we decided, if I remember. Somewhere around 1 nanofarad, in that ballpark. It won't change. Unless I change the geometry of this, the capacitance is fixed. It's a constant. So basically, you're talking about V equals just some constant times Q. Now, you've had graphs like that before. In math, you have Y equals some constant times X. And you know what that graph looks like. It's just a straight line. Y equals Kx. Well, this is going to be a straight line. Only it's going to be V equals Q over C, where C is a constant. Now remember what voltage is. Voltage is energy per charge. And what you're doing is you're taking energy per charge. What I'm trying to tell you is that the area underneath this graph is equal to your energy. And then I can show you where these equations come from. See, what voltage is energy per charge. And if you multiply by charge, guess what you'll get? The charges cancel, you'll get energy. See, these values here are joules per coulomb. And these values here are coulombs. And when you multiply joules per coulomb times coulombs, you get joules. And you guys all know the area under that graph. You could write an integral if you wanted to. It's equal to V dq. And you're multiplying joules per coulomb times coulomb. So you get joules. In this case here, you don't need to integrate anything. It's a triangle. And they taught me in school many years ago that it's 1/2 the base times the height, right? Yeah, it's 1/2. See, here's the height, it's V. Here's the base, it's Q. And this total area here, and that'll give you your energy, should be equal to 1/2 the base, which is Q, times the height. Hey, look, we just came up with this equation here, didn't we? We just came up with the energy stored in a capacitor. Now, how'd they get this? Well, remember that Q is equal to CV. So if you just take that CV and stick it in there for Q, can you see you'll get 1/2 CV times V, you'll get 1/2 CV squared. That's where that one comes from. Where does this one come up from? Well, see, V is equal to Q over C. So if you have a Q over C, you'll get 1/2 Q times Q over C. You get 1/2 Q squared over C. There's our three equations, and that's where they came from. It's in your book. You could read your book if you had to. But let's do an example, shall we? Any questions on energy stored in capacitors? Any comments or questions? We'll do a problem on that here in a minute. Well, okay, let's do a problem then. Just need a little room here to work. You're going to memorize that thing right there. I'm going to erase it here in a minute, but I want you to memorize it. That's the definition of what capacitance is. It's the amount of charge you can put on a capacitor at a given voltage. Okay, let's suppose you had a capacitor. Oops. Why did I connect them? That's not a good idea. And we're going to put we'll put our 6-volt battery here. 6 volt. What do we want here? Maybe. Well, in the lab Thursday we have a fifth. I think we have a 6,000 microfarad capacitor. Let's suppose we connected that 6,000 microfarad capacitor to a 6-volt battery. My question is, there's going to be energy stored in that battery. Oh, gee, I erased the equations, but I had them there, and you guys take excellent notes. Just look at your notes. There's 3 different equations you can use. I'm going to shut up and see if you can find the energy stored while I take a break. Go for it. Find the energy stored in that capacitor. Well, I got an answer. Here, I'll help you guys. Probably the easiest equation to use is this one here. Because see, we know the C. The capacitance is 6,000 microfarads, and we know the V. You know you're going to have 6 volts. Put it in your calculator, and let me call on one of my very best students here. Jacob, unmute and say hi.
Hello.
Hello. Jacob, have you got this energy stored yet in that capacitor?
I'm doing it right now.
Take your time. Take your time.
What units is the energy in?
Yeah, what are the units of energy?
Joules.
They're joules. They're joules. Good going.
108,000?
I got 108, but I don't know about 1,000. I like your number.
No, I see what I did. 108.
I like the 108, but you still don't have the decimal in the right place.
No, I forgot the micro.
Yeah, so what do you think it is?
108.
Well, how come I'm getting 0.108?
That's what I got too.
Me too.
I think it's 0.108. Do it again. Now remember, micro is 10 to the minus 6. Go 6,000, 10 to the minus 6 times 6 squared. You have to square that. Who was I just talking to? Was that Jacob?
About which one?
I don't know. I'm getting 0.108 joules. I think that's the answer. How about you guys?
Yeah, that's what I got now.
Yay, good going. Excellent. Well, let's do one a little bit harder. That was fun. We'll do one. Are you okay with that, everybody? Here's your chance if you didn't understand it.
How did you decide which equation to choose?
Oh, well, we could use another one. Thank you for asking. There's
I
one.
mean, more or less, it was kind of asking how did you go into that decision-making process about which one was the easiest one to use?
They all work. Let's do all three of them. It won't hurt us any. Look, there's one that goes like this. Now the thing is, we have the voltage. And that was who was that I just talked to? Was that my friend?
Phoebe?
That's Phoebe. We have the voltage. But we don't have the charge. But we can get it.
Oh, I see. Yeah. Okay.
You don't need
That
my
makes
help.
sense then.
She
Yeah, I
doesn't
got
need-
it.
She doesn't need me anymore.
No, you're fine.
Okay, well, I'm going to do a little harder one now. I'm going to do a little bit harder one. Then we're going to take a little 10-minute break. I might go down and see what there is in the refrigerator. I don't know. Let's suppose this is going to be a little bit harder. We'll put a 6-volt battery here, and we'll put our old buddies, our 3 microfarad capacitor C1 and 6 microfarad capacitor C2 in series like that. And what I need to know is, I need to know what the energy is in each one. Now that's a little harder, isn't it? That's a little harder. I'm going to shut up and let you work on it though for a minute. Well, I kind of want to take a break here, so let's go ahead and finish this and we'll take our little break and I can scrounge around in the refrigerator there. The thing is, we did this problem earlier tonight, and if you took notes, you'll remember what those voltages were. Do you remember the little guy got the 4 volts and the big one got the 2 volts and they added up to 6 volts? We did that, didn't we? If you forgot, we'll go over it again. If you forgot, see there's an equivalent circuit that looks like this. Where you can replace this with a 2 microfarad capacitor. And how did you get that? By taking 1/3 plus 1/6, and you'll get a 2 there when you solve that. And so the charge on here will be Q equals CV. If this is 6 volts, and that's 2 microfarads, then you're going to get 12 microcoulombs on there. And the thing about series is you're going to have 12 microcoulombs on both of these because in series, the charges are the same. You might want to write that down someplace. In series, the charges are the same. In parallel, it's the voltages that are the same. Can you read my writing? That says 12 microcoulombs. Okay, well now once you got that, you know the volts and you know the charges and you know the capacitances. You can use any one of those 3 equations and get the energy. I'm going to shut up again now, and you go ahead and get the energy, and we'll put that on there. Take one of those 3 equations and find the energy. Anybody have the energy on this one yet? The stored energy. See, it's storing energy in electric fields. Remember the equations, there's 3 of them. One of them just goes like this. You could use that one. We know the charge and we know the volts, or you can use the other 2. Let me ask somebody. How about my friend Christy? Help us. Christy, what did you get for the energy stored in that capacitor?
Well, I was looking for like the total energy, so I think I did something wrong.
Well, that's okay. You can get the total energy. You could get that from here. What did you get for the total energy?
I got 3.6 times 10 to the negative 5th joules.
Man, I don't think that's right.
Yeah, I don't think so either.
You might be right, but here, tell you what, let's do it this way. Take 1/2 of Q, which is 12 microcoulombs, times V, which is 4 volts. Do you get, What, did I do that right? The Q is, yeah. And then, no, you might have been right. I might have goofed up. Do you get 24 microjoules stored in this one? I think that's right. Or you could use this other equation. You could go, the energy is equal to 1/2 CV squared. Let's try that. Take 1/2, does all that show up? Yeah, pretty good. Take 1/2 of 3 microfarads times 4 volts squared. If you do that, what do you get?
Can you tell me again how you decided that the 3 microfarads got 4 volts and the 6 microfarads got 2 volts?
Oh, yeah, absolutely. Great idea. Let's do that. We know that there's 12 microcoulombs. You can get that from here. See, the dirty little secret is to make this simplified equivalent circuit. You can get the charge. Now, once you got the charge, the volts is equal to the charge divided by the capacitance. If the charge is 12 and the capacitance is 3, what's 12 divided by 3?
4.
It's 4. Yeah, it's 4 volts. That's right. Now here, what's 12 divided by 6? By Jove, 12 divided by 6 is 2. Christy, that's how you get the volts. Did you understand that time?
Yeah, I think I just totally missed something.
That's okay. That's what we're here for. Well, I think you get 24 either way you do this. Let's see. Yeah, 8 times 3 is 24. 6 times 4 is 24. There's a third equation. Do I have room to write it? Maybe. The third equation goes 1/2 Q squared over C. Let me try that. What's 1/2 of 12 microcoulombs squared over 3 microcoulombs? I don't know. Yeah, gee, it's 144 over 6, isn't it? What's 144 over 6? Boy, Jove. You know what? It's 24 microjoules. You get 24 microjoules no matter how you do it. You get the same answer each time. Now let's get the energy stored in this one. Well, how would you do that? Same old boring stuff. You could take 1/2 of the Q, which is 12 microcoulombs, 0.5 times 12, times the volts, which is 2. I wonder if I did that right. I'm getting 12 microjoules on
That's
this.
what I got.
Yay, good going. Now, the total would be 12 plus 24. It should be 36. We should get, in this equivalent circuit, we should get 36 microjoules. Let's see if we do. I don't know, take one of these equations. There's 3 of them. I'm going to take 1/2 times the 12 microcoulombs times the 6 volts. Let's see, I did something wrong. 1/2 of the 12 microcoulombs times the 6 volts. Boy, Joe, I'm getting 36 microjoules. Well, see, that's the total. You get 24 on this one, 12 on that one. They add up to 36. Okay, we're going to take a little 10-minute break, and we're going to come back and have more fun talking about capacitors. And we'll work some more we'll work some problems. That'll be good. Okay, take a break. You probably need a break. This stuff is fun, but I don't know if it's that much fun. Okay, I'll be back. Okay, it's 7 o'clock. 10 after we'll resume. Go stretch. Oh, you're up there. I was looking for you, and you weren't in your chair.
Well, I know I'm in a lot, but I'm gonna look elsewhere in your clothes, but it's maybe behind.
Your clothes, so
So you're on break?
yeah, I gave it.
Water in your body.
Everybody go forward.
Talk again. Yeah.
Okay. We're going to get back to work here. Let's work a problem out of the book. All right, we're going to work a problem out of the book here. Now this is 839. Let's do that. Looks kind of hard, actually. But between us, we can do it. 839. Now let me find it. Well, I didn't find anything to eat in the refrigerator, but I did feed my dog. She's 12 years old, but she still gets around pretty good. She wags her tail when I go out there. Okay, let's do this 12-139. Now it says a 2 microfarad and a 4 microfarad capacitor are in series across a 1 kilovolt. Okay, let me do that. 2 microfarad and 4 microfarads. Are in series, that's series, across a 1 kilovolt You know what that is? That's 1,000 volts, isn't it? It's a kilovolt. The charge capacitors are then disconnected. We'll do that in a minute, but first let's see what's the charge is going to be on each one and the voltage on each one. We'll do that and then we'll disconnect them like they said. The first thing we have to do is the dirty little secret of solving these capacitor problems is we have to make this equivalent circuit. We have to simplify it. See, we're going to make it simpler. But to do that, you're going to have to find what this equivalent, we'll call it the equivalent capacitance. And I'm going to shut up for a minute. I think we're all back. Let me see if most of our, oh yeah, we got a good crowd that came back after the break there. I'm going to shut up and I want you to find what that equivalent capacitance is. Go for it. I think I know what it is. Let me ask somebody here. Somebody that I haven't called on yet all night. I don't remember if I called on Zach. I think I spoke to him. Zach, do you have what that equivalent capacitance is?
I'm still working it out.
Yeah, that's okay. Take your time. Take your time.
Wait, is it 4/3?
Yeah, that's what I got. Good going. You know what it is? It's 4/3, like Zach says. Or you could say 1 point. Is 4/3 the same thing as 1.333?
Yeah.
Yeah. Now watch it though. It's microfarads is what it is.
Well, it was 4/3 to the -1 would be.
Here, let's.
Oh no, 4/3. You're right. You're right. You're right.
You're
That's
okay.
right.
Oh,
I've got it flipped around in my head. I'm sorry. Tired day.
That's okay. No thank you point though yet. No thank you point for that yet. Next time.
No, because it was actually 3/4 to the -1 would be the 4/3.
That's absolutely right. I'm glad you spoke up because there's other people doing the same mistake. Okay, well, good. Now we can get the charge. See, the charge is equal to CV, so we can get the charge. Now remember, this is 1,000 volts. Hey, I can do that in my head. So what's the charge? Well, I can do it in my head. Is it? It's 1,000 times that, which makes 1,333 micros. Could you call that 1.333 millicoulombs. How about that? I need an uh-huh. Did I do that right?
Yes.
Okay. So you see what that means is, that means this here is 1.333 millicoulombs. And this one here is 1.333 millicoulombs. Now we're going to get the voltages. And you know how to do the voltages. You go Q over C. You got the Q, you got the C, and we're going to get the voltages now. I like to put them in red. Let me get my red color here. We're going to put the voltages in red. So you take the Q, 1.333, what is that, e to the minus 3 actually, and then you divide by 2 e to the minus 6. I'm getting 666.5 volts. How about you guys? Now I'm going to do the other one. I'm going to take the Q, which is the same. They're in series. 1.333 e to the minus 3. And I'm going to divide by 4 e to the minus 6. And I'm getting 333 point. You know what? I bet it's 3 if you round it off, volts. And I bet this would be a 6 if you rounded it off. Now see, if you add those two up, don't you get 1,000? Well, you get 999.9. That's pretty close to 1,000. So we've got it figured out what will happen. Now let's keep reading the problem. We're just getting started. If you just came back from a break, we're doing 839. And we're following their directions here. Then we're going to disconnect them from the source and connect them to each other with the terminals of like sign together. Okay, let's do that. So what we're going to do is we're going to come along here and disconnect. See that 1,000 volt source? When you disconnect that, you still have this voltage on here, though. You still have that voltage there, but the source is gone. And you still have this charge on that one. And you still have that same charge on that one. They didn't go anyplace. Those charges did not go anyplace. Where are they going to go? You've disconnected it. They can't go anyplace. We don't need this one anymore. And that's what we have. And then what they said was they're going to connect the positive. They're going to connect them, disconnect them, and could reconnect them. See, this is positive, and this is negative, and this one's positive, this one's negative. And we're going to reconnect them. Now let me do that. Let's see if I can do that. Right now, the negative on this one is connected to the positive on that one. That's not what they want. They want you to disconnect them. There, I disconnected them. And then they want you to do this. We're going to take the positive one here. And what we have is 1.333 millicoulombs. And this one here, this is the positive one. It's got the same 1.333 millicoulombs. Now we haven't connected them together yet. We're going to, But let me put the voltages on there, what they are right now. See, this one right now has 666.6 volts. This one has 333.3 volts. And we know the capacitors. This one is the 2 microfarad. And this one is the 4 microfarad. And here's what we're going to do. We're going to connect these, and we'll put a switch right here. Now, when we throw that switch, right now, that's what we've got. Those charges haven't changed any. Of course, the capacitances are constants. They cannot change. The voltages are what we have there. But when we throw this switch, what's going to happen? Something's going to happen. And let me ask you, what do you think will happen when you throw that switch? It's in parallel. Well, what do you know about parallel? In series, the charges are the same. In parallel, what do you know about parallel?
The charges are different.
Yeah, the charges are going to be different. What's going to be the same?
Volts.
The volts. Well, right now, the volts are not the same, are they? But when you throw that switch, I think the volts will have to be the same, because that's what happens with parallel. The volts are the same. So how are you going to get the volts to be the same? Any suggestions? How about this idea? Do you think maybe some of these charges are going to travel over here and maybe make more charges on here? Of course, that'll make that negative. And when that happens, won't the volts go up on this one and the volts will go down on this one? Isn't the volts equal to the charges over the capacitances? And see, if your charges got bigger, if this moves some charges over, won't the volts go up? And if the charges are smaller because they're leaving here and going over here, won't the volts go down? And they'll have to be the same, won't they? They'll have to be the same. Now, what's the dirty little secret in solving these problems? I've told you this about 3 or 4 times. Does anyone remember the dirty little secret for solving these capacitance problems? I'll write it out for you. Don't you want to make an equivalent circuit? Isn't that the dirty little secret? You're supposed to say, yes, Mr. Griffin. Well, that's what you do. You make an equivalent circuit. Now, there's the equivalent circuit to this when they're in parallel is a 6 microfarad capacitor. That is the equivalent circuit. And what do we know about it? Well, we know the total charge. That charge is, they can redistribute, but the total charge is going to be, won't it be 2.666 microcoulombs? It can't go anyplace. Won't that be the total charge? I mean, some of these are going to go over here. And the total is still going to be 2.666 on this side of the circuit. Now look at here. You can find the voltage if you know the charge and the capacitance. What will be the voltage if you have 2.666 microcoulombs and you have 6 microfarads? Can you read my writing? What do you get for the voltage? Well, I don't know. I've got a calculator though. It's did I do that right? You take the charge, yeah. Take the charge, which is no. This is a screw up. It's millicoulombs. There we go. It's 2.666 total millicoulombs. Why did I put volts there? That's not right. I'm making mistakes, guys. It must be getting late or something. But I think we're okay. Now we're going to find the voltage. Go for it. 2.666 e to the minus third divided by 6 e to the minus 6. What do you get?
444.33.
That's what I got. Here, let me put that in red. I'm getting 444.3 volts when you connect them like that. And when if you got the total voltage, they'll be the same on these now. So let's draw the final circuit. I need a little room here. I think there might be enough room down here. Here we go. See, we're gonna close that switch. And we figured out that we have 444.3 volts on each one. 444.3 volts on each one. And this one is a 2 microfarads. And this one is the 4 microfarads. Now let's get the charges. Well, to get the charge, you just go C times V, and we got the C, we got the V, so what's the charge here? I can't do that in my head. Would it be? Yeah, I can almost do that in my head. No, let me do it on the calculator. I'm getting 888.7 microcoulombs on that one. Now I'm going to do this one. Q equals CV. There's the C and there's the V. 4 times 444.3. I'm getting 1,777.2 microcoulombs on that one. Now, do those two add up to? No, wait a minute. Now, I'm doing something wrong here. No, I'm not. I bet that's right. Do those two add up to 1.333 millicoulombs? Let me see if they do. Okay, I'm going to add those. I'm trying to add those. And what I'm getting is I'm getting a total of 260. I don't know, my brain is mush. I'm trying to add these two, and it should give me the same total charges because they can't really go anyplace. And if I did that right, let me add those up. 1777.2.
It does give you the right answer, but it only gives you the answer of the two numbers added together.
Yeah, that's right. That's exactly right. E to the minus 6 plus 888.7 e to the minus 6. Now, when you add those together, what you get is a total of 2.666 times 10 to the minus 3 coulombs. Well, if you add these together, do you get 2.666 times 10 to the minus 3 coulombs? Yes, you do. See, you got the same total charge. Now let's look at the answers and see what the answer book says. Now this was problem 839, and it was kind of tricky. I thought it was. Let me see what the answer book says. Here we go. 839 says, 839. They said 0.89 millicoulombs. I don't see any 0.89 millicoulombs anyplace, do you? Am I doing the wrong one? Here's their answers. Maybe I don't understand. The answer book says, this is in the back of the book. They said 0.89 millicoulombs. And they said 1.78 millicoulombs. And they said 444 volts. Now we got the 444 volts. Oh, look, we got this too. That 1777 microcoulombs, that's a 1.78 millicoulombs. We got that. And look here. You know what this is in millicoulombs? It's 0.89 millicoulombs. We got all these answers. We got the answers they got, but that was tricky. Did you have any comments or questions on that? And what is the dirty little secret to solving these problems? It's the equivalent circuit. And you know the equations. Okay, well, let's go on to the last topic for tonight. It's a long night, I know. But we're in a good field. We want to be engineers or scientists, and it's just not going to be easy. Now, the last topic for tonight is this business of dielectrics. This is on page 369 in your book. And I'm going to erase this unless there's a comment or question. Anybody, comment or question? Okay, well, let me erase all that. We're going to talk about something called dielectrics. Now, when they draw these parallel plate capacitors like this, they're implying that there's nothing inside here, that it's just empty, okay? You might have some air or a vacuum, but there's nothing in there. But when I made my capacitor, do you remember I put paper in there? I filled this space with paper. And the paper serves a couple of functions. For one thing, it keeps the metal plates from touching each other. We don't want them to touch because then you'll have a short. But another thing it does is it provides stability, and it keeps the plates from, say, warping or bending. Well, it keeps them from touching. But it has even a third function. It increases the capacitance. Now, let me see if I can show you why. Let's take a capacitor that doesn't have any, they call it a dielectric. And the basic equation for a dielectric is there's this little dielectric constant times the capacitance if you have a vacuum. If it's empty, the zero represents a vacuum. You'll see that equation. It's on page 369. And you have these dielectric constants. Now, we use paper on my capacitor that I made, and we can look up the dielectric constant for paper. It's on page 376. If you look on page 376, the K for paper is, I don't see paper. Do they have paper? Yeah, they have paper. It's 3.7. Can you find that 3.7 on page 376? It's called the dielectric constant. It says if you put a piece of paper between them, you get 3.7 times the capacitance. Suppose this thing here was a 1 microfarad capacitor before you put the paper in. After you put the paper in, you'll have a 3.7 microfarad capacitor. It increases the capacitance. Now, why is that? Well, let me show you. Let's suppose you connect this to a battery and you charge up these plates. Of course, if this is connected to the positive of the battery, that plate will be positive and this plate will be negative. Okay, that makes sense. But we don't have the paper in there yet. Now, if you put the paper in there, let me do that in a different color. I have some green here. We're going to put some green in here. That's the paper. We're going to put the green in there. Now see, paper, it's got electrons and protons, but they're locked in. They can't move like they can in a metal. In a metal, the electrons are free to flow around and move any place they want to. But in paper, it's got electrons all right, but they can't flow. They can't really take off and go anyplace. However, they can rearrange themselves in their atoms. They can all go to one side of their molecules. And that's what they do. The electrons in the paper molecules, on every molecule of paper, they'll shift to the left. And so you'll have, we'll make some negatives in green here. I don't know if you can tell that's green. But you'll have some, there's really no electrons there. It's just that they shifted in their atoms. And if the electrons in every atom shift in that direction because of the attraction of the pluses, that makes this end of the paper molecules positive because the electrons shifted that way, making this end positive. So what you've done here, remember before, maybe I should draw the before and after pictures. Here's the before picture. This is the before picture, and you have these pluses and minuses, and you have electric field. Look, you've got an electric field. There it is. And the voltage that you have is going to be equal to E times D. Now here you still have that electric field. Those pluses haven't gone anyplace. I got 4 pluses here. I still have 4 pluses here. I still have that same electric field. I've still got that same electric field here, but now I've got a counter or an opposing electric field going this other way. It's not as strong. It's got a name. It's called the induced electric field. It's induced. Let me write that for you. It's induced. You've got an induced electric field. Field, that's not right. Field, there we go. An electric field is a vector. So what it amounts to is you've got a vector going this way that you originally had, but now you're picking up a smaller electric field going this way. That makes the total electric field smaller. Can you see that? Because it's a vector. See, you have to do a vector addition there, which amounts to a subtraction. And since this new voltage is equal to ED, the D hasn't changed any. The D is just the distance between the plates. But see, if this electric field is smaller, oops, there's 2 L's in smaller, isn't there? If this electric field is smaller, that makes the voltage smaller. When you put the paper in, the voltage goes down. It's the weirdest thing. The voltage goes down. The voltage goes down, and we have this equation that goes like this. C equals Q over V. Now this Q doesn't change any. Whatever these pluses are, they don't go anyplace. Paper is a non-conductor, so they can't conduct and go anyplace. The Q is the same. But if you make the voltage smaller, which is exactly what happens when you put the paper in. When you put the paper in, the voltage gets smaller. Now, what happens in a fraction if you make the denominator smaller? Let me ask one of my wonderful students here. I know you know the answer to this. Nicholas, if you make a fraction, if you make the denominator smaller in a fraction, what happens to that fraction, Nicholas?
The result is larger.
It makes it larger. Yeah. See, like if you make if you have 1/4, and if you make that 4 smaller, like 1/2, I think 1/2 is bigger than 1/4. Yeah, when you make the denominator smaller, the fraction gets bigger. So putting the dielectric in, In fact, if with paper, it makes it 3.7 times bigger for paper. Now, there's a whole list of those on page 376. There's other ones. There's hundreds of things. There's mica, even water. You can use water, but it has to be distilled water. Did you know distilled water is a non-conductor? But if there's any like soap or sweat or minerals, calcium, carbonate, if there's anything like that in the water, it becomes conducting and you can't use it for an insulator anymore. But there's a whole list here on that page, and paper is one of them. So we've sort of introduced the idea of dielectrics, haven't we? Okay, great. Well, let's do a problem like that, shall we? Okay, we'll do one here in a minute. Let's go back to what we learned earlier, and then we'll try a dielectric in a little bit. But first, is there any comments or questions on anything before we continue? Okay, well, let's go back to the stuff we learned earlier tonight. Let's suppose you had a circuit like this. We need to practice these equivalent circuits. We can have all of these be microfarads, that'll be fine. We need to practice this. Now, what I want you to do, I'm going to shut up and let you do this. I want you to make an equivalent circuit, a simplified equivalent circuit with just one capacitor. I want you to combine these. I know you can do it and solve for the equivalent capacitance. On your mark, and get set, go. I think I've picked on just about everybody tonight. Been a while since I've picked on Stephen though. Stephen, do you have this yet?
I think so. I'm getting 20.89 not
That's
micro.
what That's what I'm getting.
And-
I'm getting 20 point, a bunch of eights, right?
Yep.
Microfarads. Now, does anybody need help with that? Good going. I think that's right. Okay. Great. Now what we're going to do is we're going to connect up our battery. We would use a 12-volt car battery here. We'll connect up that 12-volt car battery. And what we need now is we need the voltages. Well, why don't I put them in red? We could call this V1, V2, we need the voltages. Of course, we can put in the equivalent circuit, we can put that 12 volts on there also. But we need those three voltages. I'm going to shut up again. You have a minute or minute and a half. I need those three voltages. Go for it.
Shouldn't that 20.888 be micro coulombs?
Big honkin' thank you point. Proud of you, Zach. Thank you. You helped the class. Need those voltages. Honestly, don't have them yet, so my brain isn't working too good. Maybe you got them, but I'm still working on it. Well, I think it's time maybe for us to do this together. Now this one's pretty easy. I know what this one's going to be. It's going to be 12 volts. Because it's connected directly across the 12 volts. So that's 12 volts. That's not a problem. Now these two together, though, do they make a 8.8, a whole bunch of 8s, microfarads? Isn't that what they make when you put them in series like that? I think that's right. I think that's right. And so if you want the volts is equal to the charge divided by the capacitance, right? So you take the charge, and the charge is, well, I don't know the charge. That's my problem. Charge is equal to CB, and the C is 8.888 microfarads, and the V is 12 volts. So the charge on this one is I'm getting 106 point, a bunch of sixes, microcoulombs. Of course, that'll be the same charge on this one, 106.6 microcoulombs. Now we can get the voltages. See, the voltage is the charge divided by the capacitance. So take 106 and divide it by 20, and I'm getting 5.33 volts. Now take the charge, 106.6, and divide it by your 16 microcoulombs, and I'm getting 6 point, a bunch of sixes, volts. Now the 6.66 added to 5.33, does that give you 12 volts? Yeah, it does. Yeah, it does. So we have the we've got the volts on everything.
I think I mixed the step up. How did I get to, what do we do with the 20.88 to the 106?
Oh, well, if you take these two in series, you get 8.88. Let me do it for you. There's some room right here. You go 1 over 20 plus 1 over 16 equals 1 over just these two, and you'll get 8.888 microfarads. That's where we got that. And then when they're in parallel, the 8.88 plus the 12 gives you the 20.888. Are you okay now?
Yeah, I was asking for the step after that. I was asking about, I think I'm supposed to get the volts next. I think I would use don't you use the 20.88 and the 20 that they give to get the volts?
Let's see now, wait a minute. I got lost, Zach.
I'm trying to figure out the next step. So right now I'm at the 20.88.
Yeah.
And I'm trying to remember what to do after that.
Okay.
Well,
now,
that 20.
here's
that
the
20 point.
complicated. Here's the complicated thing. That's the total charge. You have 106 going into here.
How do you figure that out?
Now, did I do that right? Is this right?
That's should be capacitance.
Yeah, that should be farads. Somebody made me change that. Shame on you. I had it right. That's capacitance. Whoever just said that, they're right. And if you made me change that, don't feel too guilty. We all make mistakes. Yeah, that's what was causing me a lot of trouble right there. But see, that's the equivalent capacitance of this whole circuit. Because if you take 8.88 and 12 add them, you get the
Right.
20.88. That's fine.
So that's C.
And then we have Zach was asking me how I found something. Zach, I got lost.
106.
What are you asking?
I think now that I understand that that's C, I should be able to move forward.
Say that again.
I think I should be able to move forward now that I understand that is C instead of something else.
Yeah. I think I got mixed up there somehow. But I think we're
You're
okay.
using your brackets.
Brackets?
Yeah.
Yeah. Gotta watch those stinking brackets. Okay, well, that was a lot of fun. Now let's do one with energy. We had some practice on that.
Hold on, wait, I'm still writing.
Oh, yeah, go ahead. Now, did we get everything? We got the charges. Yeah. Did we get the
I
charges
still
on
don't know
this?
how we got to the 106 though.
You don't know how we got the 106?
Yeah.
Here's how you get that. Q is equal to CV. Now, if you have 5.33 volts and you have 20 microfarads, that's the C, that's the V, you multiply them and you get 106.
Okay.
That's where we got it. This can
All
be
right.
confusing, for sure. Did we get the charges on this one? Q equals CV. What's the C? 12 microfarads. What's the V? 12. Well, that gives you 144 microcoulombs on this one. Now the total, if you add that to that, what does that make you? I don't know. What's 106 and 144? Don't know. But my calculator does. 106. 106.6 plus 144. I get a total of 250.6 microcoulombs. That's what you should get with this one. Let's see if you do. Q equals CV. Well, here's the V and here's the C. What's 20.88 times 12? Should be this, is it?
Yeah.
By Jove, it is. See, that's the Q. We got the Q, we got the V, we got the C on everything. Okay, let's do one with energy now. We had some practice with that, and that was kind of tricky. Any last comments or questions? Okay, well, let's do one with energy. Here we go. Now let's have our 12-volt car battery here. And we'll connect it up to a in the lab, we've got some 6,000 microfarad capacitors. And what we're going to do is we're going to find the energy stored in that capacitor. There's three equations for it. And I'm going to shut up for a minute. You got a minute. Can you read my writing? That's supposed to be a big U. Find the energy stored in that capacitor. got what I think is the energy stored in that capacitor in joules. Daniel, unmute and say hi. Uh-oh, Daniel taking a break maybe. I don't
Oh, I'm
know.
still working on it.
No, there you go. That's fine. Keep working. I think I've got the joules on it. Here, let me put them in brackets. I think I know what the joules are. How about somebody out there? What'd you guys get?
0.432.
That's what I got. I got 0.432 joules. Now, you can do it several different ways, but does anybody need help on that? See what I did? I just went 1/2 CV squared. We know both of them. I know the C. That's the C right there. I know the V. That's the V right there. And that's what I got. Now we're going to do this. This is going to be about the last thing I want to do tonight. I think I've had it. We're going to come along with a piece of paper and we're going to stick it in here. See, this is the before picture. Here, let me draw the after picture. We're going to take that same capacitor and we're going to put the paper in. It's still 12 volts here. But when you slide this paper in, and remember, the paper has a, what do they call that? It has a dielectric constant. I forget, was it 23? What was it? Does anyone remember?
Wasn't it 37?
Let me look it up.
3.7.
It was 37?
7.
I don't remember. Let me look it up. Somewhere, yeah, here we go. Paper. 3.7. There we go. Good thinking. You got a better memory than I do. It's 3.7. So when you put that in there, the capacitance goes up. I explained that. Remember, you might have slept through it, but I explained about the electric fields and the voltage getting smaller and denominators getting smaller. And the capacitance goes up. So now the capacitance is 6,000 times 3.7. I'm getting a capacitance in this circuit after you put in the paper of 22,200 microfarads. Boy, it really went up, didn't it? That's a comma. We'll just leave the comma out. Now I want you to find the energy stored in the find the energy stored in the capacitor now. Okay, I've got what I think is the energy. This is before and after you put the paper in. Hey, the energy went up, didn't it? The energy went up, and how much is it now?
1.6 joules.
Yeah, good going. 1.6 joules. It was just 0.432 joules, and now it's gone up. Where did that extra energy come from? Does anyone have any idea? Where did it come from? It had to come from someplace.
In the paper.
It came from where?
That K constant for paper.
No, energy doesn't come from paper unless you burn it. I guess you could burn it and you could get some energy. No, where did the energy come from? Energy doesn't just show up. It has to come from someplace. Where'd it come from? You guys are going to feel silly when I tell you.
It's already there.
No, it's not already there.
Well, you took the paper can't. I don't know. Insulated the.
Okay, guys, I'm going to tell you the answer. The energy came from the battery. The energy came from the battery. So you got a battery here. It's pushing electrons in here. Doesn't the charge get bigger? Let's find out what the charges are. And see, that had to come from the battery. Let's find the charges here. You know how to find that. You go Q equals CV. So I'm going to do that now. 6,000 microfarads times 12. 0.072 coulombs. So that's the charge on this one. Did I do that right? Q equals CV? I think so. Now let's find the charge on this one. Q equals CV. All right. 200 e to the minus 6 times 12. I'm getting 0.2664 coulombs. Hey, we got more charges. Where did the energy come from to push those charges in there? Well, it came from the battery. That's where it came from. Battery is providing the energy here. Hey, I got 4 minutes left. Let me show you this now. Forget this one. We'll just erase that one. Let's disconnect this battery, shall we? We're going to disconnect this battery. This is the last thing we're going to do tonight. I'll tell you what we got here. We got a disconnected capacitor. It has a capacitance of 22,200 microfarads. It's got a charge on it of 0.2664 coulombs. It's got paper in it with a dielectric constant of 3.7. And what we're going to do is we're going to pull that paper out. Just grab it, put a little string on it there, and pull it out. Now here's what you got now. There's no battery now. Here's what you got. There's no battery, but these charges are the same. They can't go anyplace because, remember, paper is a non-conductor. You still have 22,200 microfarads. Now, I'm sorry, but I think I erased my energy stored in the capacitor. Let me get that again. I think I erased it. Oh, gee, am I running out of time? The energy is 1/2 Q Q over, 1/2 Q squared over C. So we got the Q, we got the C, and the energy stored is 1/2 times 0.2664 divided by 22,200 e to the minus 6. Did you get 6 joules? I wonder if I did that right. Let me do it again. 1/2 times 0.2664. You have to square it though, right? Divided by 22,200 e to the minus 6. No, that's not right. I'm getting 1.59. I think we did that before. Somebody rounded it off to 1.6 joules. Now, over on this one, we got the same charge, but now the capacitance here, remember, is smaller. It's it was before we put the dielectric in there. Oh, I'm running out of time. I'm gonna have to let you guys go. Remember, it was 6,000 microfarads, wasn't it? Yeah, that's what it was. So what's the energy stored in it after you pull the paper out? Well, it's 1/2 Q squared over C. We got the Q, we got the C. So help me find the energy stored after you pull the paper out. Here we go. 1/2 times 22,200 e to the minus 6 divided by 6,000 e to the minus 6. I'm getting 1.85 joules. Gee whiz, we got a little more energy now after we pull the paper out. Where did that energy come from? It didn't come from the battery because the battery's not there. You pull that paper out and the energy went up a little bit. Not much, but it went up. Where did the energy come from? A mystery for you to worry about. We're going to have to quit. It's time. I hope you enjoyed that. We covered a lot of stuff. I think there's some homework. Check on Blackboard, do your homework, and I will see you on Thursday. Goodbye, everyone.
Goodbye.
Bye.